Hey guys, I know this is a little bit different type of instructional video. I've never actually done one of these before, so we're kind of learning on the fly. I was looking back through your Khan Academy scores and I saw that we really struggled. If you're looking at my screen here, we were good with the graphing probability, okay with probability discrete, but we really struggled with this interpreting expected value one. So I'm going to kind of do the exercises, I guess, myself and kind of talk you through what I see, what pops out, and hopefully it'll help you go back and reattempt and get those a little better. So you kind of get a window into my brain. All right, so we'll jump right into the first one. A head coach needs to decide whether or not to move forward with a given strategy. Their assistant coach says, based on previous data from similar situations, the expected return if we move forward with this strategy is 4.6 points. All right, off the bat, let's just do a quick review what expected value is. Expected value is the long-term average. It's the average of a probability distribution. So when I read, if we move forward with this strategy, then we'll get 4.6 points. I'm expecting that if we implement whatever that strategy is a bunch of different times, like over the long run, like thousands of times, on average, it's going to get us back 4.6 points. The assistant coach says if we made this decision in scenarios like this many times, then the average would return would be about 4.6 points. Okay, the head coach said if we move forward with this strategy, then we will get 4.6 points. So again, using our idea of expected value, hopefully you kind of see really clear here what is and is not the answer. Expected value is the long-term average. Okay, so when we read based on previous data from similar situations, the expected return is 4.6 points. This does not mean if we move forward, then we will get it. Expected value isn't a guarantee. And in fact, probably if it's a discrete distribution, it's not even possible to get 4.6 points. Typically with discrete, you could only get 4 or 5 or 6 or 7. That's not what this is saying. What this is saying is what the assistant is saying. If we made this into scenarios over many times, on average, we would get about 4.6. So for me personally, I'm cool with what the assistant says, not as cool with what the head coach is going to say. So I'm going to go with B. We'll check it. Hey, we got one right. Okay. Josh and Adelina are staff members for a political candidate considering hiring callers. Josh and Adelina define X. Okay, that's our variable, so to speak. We worked with that back in 6.1. Okay, it's our discrete random variable. It's the amount donated by a given voter they call. Based on data from their volunteers call, the expected value is 18.07. Again, I'm not even going to read the next part next. Here's what's rolling around in my brain. It's the long-term average. It's the idea that if we call a ton of different voters, okay, over the long run, the average amount that they're going to give is 18.07 or $18.07. So let's see what Adelina and Josh say. Adelina says, for every 100 voters we call, we can expect to bring in about $1,000, 807. Okay, so for everyone we call, we can expect to bring in about, this is a good interpretation. We're just kind of advancing it to some number of voters. Well, the statement itself to me sounds good, right? They're saying for every 100 voters, we can expect about this amount. Again, the keyword being about there. She's not guaranteeing they're going to bring that in. It's by saying about and expect, we're picturing more of that long-term average. Let's just go ahead and make sure their math is correct. Okay, so if the statement above is saying, hey, the expected value, which is a donated by a given voter. So if we're expecting an average of 1807 per voter, we can take that 18.07 and multiply it by 100. And we do get 1807. So right now, I am okay with Adelina's statement, right? If on average we're getting 18.07 for voter, it's not unreasonable to think that we would get about $1,000, $1,807 for every 100 voters. Okay. Let's look at Josh's. If we call a very large number of voters, the average will be close to 1807. Again, here's what I love about this. It's the long-term average. Josh is saying we call a bunch of people, on average, they're going to donate about that much. I love both statements here. I'm going to go with both. Hey, we're 2 for 2. All right, let's move on to the next one. Tom and Rosie are designing a game. Each turn, we roll 5 6-sided dice. We're summing them. Okay, the lowest possible is 5, max is 30. So we could get any value in between 5 and 30 if we roll 5 dice and we add them all together. They let X, okay, X is going to be the sum. That's a keyword. So they're going to add together all 5 rolls, and they find the expected value is 17.5. Again, automatically expected value, I'm thinking long-term average. I'm not thinking that if I roll 5 dice, I'm going to get 17.5, or that's the most likely. What's running through my brain is if I say roll 500,000 times and I look at all those sums from those 500,000 rolls, the average amount that I get would be 17.5 points. So let's look at what they're saying. Tom says a player will most likely get 17.5 points in any given roll. Okay. Well, this is tricky. It's really close to being good, but there's something a little off here. Here's what would be an okay statement. A player will average 17.5 points, or maybe saying we could expect a player to get about 17.5 points. That's great. Here's the problem with this one, the phrase most likely. What I don't love about the phrase most likely is it says, hey, it makes you think that if I rolled this 10 times, like 6 or 7 times, I'm going to get a 17.5. That's not true. In fact, it's not even physically possible to get 17.5. You could get 17 or you could get 18 if you roll 5 dice and add them up. You can't get 17.5. So saying I will likely get that amount, that's not, I'm not likely to get that one at all. It's not possible. Rather, a more appropriate statement would be saying we would expect a player to get about 17.5 points in any given roll. Or the best way of saying it would be in a large number of rolls, the average sum or the average amount of points we would expect is 17.5. So Tom's is no good. Okay, they're not most likely to get 17.5. In fact, it's not even possible to get 17.5. Let's look at what Rosie's saying. Over 100 turns, so we're thinking about a large number of times doing this, we can expect a total of about 175 points. This is kind of like Adelina's wording. I like the wording of it. Over a long run, we're expecting an average of this. Let's just check her math here, right? What our initial says is that in a given turn, we can expect about this many points. We can expect about 17.5 points in a given turn. Well, what we need to do is if we can expect that amount or about that amount in a given turn, then for 100 turns, we just need to take that 17.5 and multiply it by 100. And that's going to give us the amount we would expect roughly. Again, no guarantee, but roughly what we would anticipate a player to get in 100 turns. Well, when I multiply 100, Rosie did some bad math. When I multiply 100, I'll show you my screen. When I multiply 100 by 17.5, I actually get 1750, not 175. So while her wording is great, her math is a little off. Over 100 turns, we can expect a total of about 1,750 points. Not 175, because again, 100 times 17.5 gives you 1750, not 175. So I'm actually going to go with neither is correct here. Final one. Richard and Cameron buy a carton containing 6 eggs. The back of the carton says the expected number of broken eggs per package is 0.12. Okay, so again, what we're saying here is obviously you can't have 0.12 of a broken egg. Rather, we're saying the average amount of broken eggs per package, if we looked at a ton of packages, would be about 0.12 per package. So let's see what we're saying here. What's Richard say? The probability that one of these cartons contains a broken egg is 0.12 on average. The probability that one of these cartons contains a broken egg, okay? Well, that's not really it. Expected value isn't a probability, it's rather an average. It's a long-term average. We would have to, the probability that one of these cartons contains a broken egg, that's more looking at the physical distribution, where we would have 0 and 1 and 2 and 3 and 4 and 5 and 6 amounts of broken eggs. And then there would be a probability for each of those. And then we would look at the probability below the one broken egg and say that's what the probability is. That's not what expected value does. Expected value doesn't tell us the probability of one broken egg. Expected value says, hey, in a long-term average, about how many eggs can we anticipate to be broken. So I'm not cool with Richard's statement. Let's look at Cameron's. For every 100 packages like this, we'd predict about 12 broken eggs in total. Again, we're kind of getting at that long run average. What we see here is they buy a carton containing 6 eggs. So the expected number per package is 0.12. So for 100 packages, if we take 0.12, because that's the amount we expect, the average amount per package, and we look at 100, 0.12 times 100 does give me 12. So if we're saying the expected number of broken eggs per package is 0.12, or the average number of broken eggs per package is 0.12, then for 100 packages, we are going to anticipate about 12 broken eggs. So I'm cool with Cameron's, not as cool with Richard's. I'm going to go with only Cameron's, and we got it right. Folks, I know this didn't hit every problem you had. Hopefully, though, it gives you a little bit more insight into kind of my brain and the way I work through these things. If you're still stuck, let me know, and I will happily help you one-on-one.